Let's get started. Thank you so much for coming to Seismo Lunch with all these other talks going on. It's my really great pleasure to introduce you to Jiuxun. Jiuxun, let's see, should be able to see him. Okay, Jiuxun is a golden grad student who graduated and is now postdoc at Caltech. Jiuxun was one of my first PhD students at Harvard and did an amazing dreamlike PhD working on subduction zone earthquakes, kind of looking at all the dynamics of subduction zone earthquakes, like kinematic representation, dynamic rupture models of shadow subduction zone earthquakes. And we've looked at a tremendous body of work on back projection, kinematic source inversions, and whatnot, synthetic word. And the last chapter of Jiuxun's PhD was before last chapter, because it's got many, but nice compilation. It was a AGU Advances paper where we looked at the depth dependence in radiation frequency. It's seen in back projection and explained with a very nice 2D simulation work. So Jiuxun has been extremely productive. And while doing this, also did a super cool machine learning model for denoising. So really amazing PhD. I was so proud that he checked all the boxes, and me returning to NSF said, yes, on those grants, yes, yes, another paper, yes, another paper. It was just fabulous. And you've learned a lot. You were fantastic in the group. And you moved to Caltech as a SCSN postdoc to look at DAS and early warning. And so it's been 1 year. And we're finally in person, actually. We're going to celebrate Jiuxun's PhD defense on Thursday. But I'm really excited to see what you've been up to at Caltech. So thank you for making the trip and the break during these workshops.
Thank you, Marie, for the great introduction. And hello, everyone. And actually, this is my first in-person presentation out of my workspace. So I really appreciate the opportunity. And yeah, so hello, everyone. I'm Jiuxun, okay, and I'm a postdoc at Caltech now, and now I mainly work on DARS. So today I'm going to talk about some of my recent study on earthquake magnitude with stars. And in this study, we propose a database and a transferable scaling relation, which can be used to estimate earthquake magnitude directly from DAS measurement. So as you can tell from the author list, so this is a collaborating work with many people get involved. So, and our group at Caltech mainly like process data and connect the data, DAS data from different regions in California. And we also get some data, submarine DARS data from the groups in Japan. And also Zach Spica's group at University of Michigan helped a lot with like processing the submarine DARS data. So yeah, so I believe most of you already heard about DARS technique here, but for those who are not familiar with that, I will briefly introduce how this technique works. So DARS is short for distributed acoustic sensing, and it's an emergent technique and optical sensing technique. So it can convert an optical fiber cable into a very dense sensing array. And we simply need to connect a DARS interrogator unit to a cable. And this interrogator will keep sending laser pulse. And so the laser pulse will travel in the fiber. And because of the small scale inhomogeneity of the optical fiber, so the laser pulse does not only like travel in one direction. So meanwhile, it also got back scattered because of the really scatter. So the DAS interrogator will also keep recording the back scattered energy and measure its change. So if there's no deformation or no strain along the cable, so the back scatter power will be basically constant or doesn't change. But if part of the cable got deformed or sense some strain, so we can detect, the interrogator can detect the change in the phase information of those backscatter power. And by calculating the difference and converting that, so it can measure the strain along the entire cable with very high spatial resolution, like meters of spatial resolution. So here I'm also showing you an example, an earthquake signal recorded by a DAS cable in Chile. And you can see for this example, we can see clear P wave and S wave. So the DARS is very sensitive and can like kind of like a revolutionary technique to provide us this very high spatial resolution sensing array. And one great advantage of DARS is that it can directly use pre-existing telecommunication cable. So here on the map, I'm showing you the telecommunication cable map in the United States. So you can see it actually have very good spatial coverage and cover many remote area and also in the offshore area. So if we can convert those cable into a sensing array, so basically we can like monitor some remote area, and the DARS can fill the gap of current seismic network in remote area. So it's a very promising technique, especially for applications such as earthquake early warning in the offshore area. So what can DARS give us? So what can we get from this great technique? So here I'm showing you a few examples. Oh, sorry, I forgot to mention. So please feel free to interrupt me anytime when you got questions, so we can I can answer the question. So yeah, what can DARS give us? So here I'm showing you a few examples. So we can use DARS can record clear seismic signal. So here is one example showing you that the different earthquake signal recorded by DARS, and it gives us very accurate phase arrival time. And you can see it's matched quite well with the arrival time predicted by some velocity model. And also we can use the ambient noise signal recorded by DARS to do ambient noise cross correlation, and which can further help us to like constrain the seismic structure or to monitor the velocity change. And also DARS can record different type of ocean waves, which can help us better understand what's happening in the ocean. And this is another example, very interesting example. So DARS is very sensitive and it can record clear traffic signals. So here shows you an example of the Rose parade in Pasadena, California. So you can see we can use DARS to track the motorcycle or the float and so it's very sensitive and can help us monitor the traffic signal. And basically DARS can provide us very accurate phase information. So with the accurate phase information, we can use that to detect earthquake. And so here I'm showing you an example using template matching applied to DARS data. So with that, we can detect more earthquake. And using the phase information, we can also use that to constrain the earthquake, the seismic velocity. So here, another example, they use the Ridgecraft DARS array and using the ambient noise cross correlation with DARS data to get a very high resolution subsurface velocity structure along that cable. And we can also use the amplitude information of DARS. So mostly people we can directly convert the DARS string to ground motion. So in this way, so we can convert the DARS array to measure the ground motion. So theoretically, we can simply multiply phase velocity to the string recorded by DARS to convert that to ground motion. So here I'm showing you an example, the Porotomo experiments at Brandley Hot Spring in Nevada. So in these experiments, people deploy both DARS array and a collocated nodal array. And so in this way, they can compare the signal recorded by two different arrays. And they find that through this conversion, the waveform recorded by DARS matches quite well with the signal recorded by collocated nodal array. And so, however, this direct conversion is often like challenged due to the uncertain apparent phase velocity. So this C here, there is often like has large uncertainty, and we also we don't know the instrumental response and coupling. So this is the main challenge using the DARS amplitude information. So yeah, right.
Is that the phase velocity or the apparent phase velocity?
Apparent phase velocity. So that's actually
It's
can vary a lot, yeah, along.
continuously, like when you're in the scattered part of the wave field,
Mhm.
continuously evolving as you get phases arriving with different wave numbers.
Yeah.
Is that right?
Yes, yes.
Yeah,
And so
Jiuxun,
here I'm showing you some
Jiuxun.
comparison from the same experiments. So in this study by Miro and Jan, so they take the measurement from the nodal array, and based on that, so they can reconstruct the wave field in this area. And so they can basically calculate the wave field strain rate along the DARS cable. And so they can directly compare what they reconstructed from nodal array with what DARS really measured. And they find actually the comparison shows a factor of 2 in the amplitude difference in some part of the DARS array. So that basically means direct conversion is very challenging, because this part of channel may have very different, may have band coupling, or the phase velocity is not well constrained. So basically the main challenge, as I mentioned, so it's still very challenging to use the DARS amplitude, especially when we want to directly convert that to ground motion. And here's I'm showing you another example. So in this early study, so by Aljo Franklin, so they compare the earthquake signal recorded by different DARS array. So this array are installed in different methods, and they find that even for the same earthquake, the signal recorded by DARS can vary with the installation of the DARS. So either for the waveform or the frequency components. So basically, this if we change the different installation method of the cable, so it can also change the waveform. So this basically the instrumental response and the coupling are often unknown. So these are very hard to get to know. So we can hardly quantify those effects into the waveforms. So we need to find some new method to better use the DARS amplitude. So that's the motivation of this study. So we are trying to answer this question. So how can we use the amplitude information of DARS, and specifically for seismological applications? So can we use the DARS to constrain earthquake magnitude? So in this study, we apply a data-driven scaling analysis. And essentially, DARS array is a dense array of strain meter. And so, yeah, and we by looking into literature, actually recently people begin to like study the scaling from conventional strain meter. So in this study by before, so they look at the conventional strain meter and they compile the earthquake waveform recorded by many strain meter, and they measure the peak strain, and then search for a scaling relation between the strain amplitude and the distance and the earthquake magnitude. So their results show that actually the strain follows a scaling relation quite well. And with the scaling relation, so they can, once they get this coefficient, so they can directly use the strain to estimate earthquake magnitude. So here I'm showing you their results. So they show that using the scaling relation, the peak strain amplitude can give very accurate estimation of the earthquake magnitude with the error within like half unit of magnitude. So this highlights that we can use the strain to estimate earthquake magnitude. So because DARS essentially records the strain, so that also works for DARS. So yeah, so this is what I just talking about. So DARS can be regarded as an array of strain meter. And one good thing about DARS is it can provide us very large amount of measurements in the peak strain rate. Basically, each DARS array often consists of thousands of channels. And for each earthquake, we got thousands of measurements on its peak amplitude. And we have lots of earthquake as well. So in this way, so we can get like tons of measurement for us to constrain and to feed for a robust scaling relation. So here I'm showing you another example of M4 events recorded by our Ridgecrest DARS array. And so basically we apply a data-driven scaling analysis on DARS peak amplitude. So we directly measure, given an earthquake, we directly measure the peak P wave amplitude and S wave amplitude. And from the earthquake catalog, we already know the catalog magnitude, mostly local magnitude for that earthquake. And we also know the location, so we can get the distance from that event to the DARS array. So with all this information, and we can use our data to feed for this scaling relation, which for now is a very simple and general scaling relation, a linear relation in log scale. So E here is our peak DARS strain rate amplitude, and A is the magnitude coefficient, B is the distance coefficient, and to account for the regional side effects, we also need to feed for a channel specific site calibration term. So that's the KN here. So this is basically our workflow. And so we first look at our DARS array in California. So our group has deployed multiple DARS array in California. So in this study, I will mainly look at these 3 different array. So first one is the Ridgecrest DARS array. It was deployed just right after the 2019 Ridgecrest earthquake, and it has recorded lots of aftershocks after the Ridgecrest earthquake. And we also have 2 longer DARS array in the Long Valley area in California. So it's deployed around the Mammoth Lake, and this is another active region. And so this is a longer DARS array and has also recorded many earthquakes. So in total, this 3 DARS array has recorded over 2 years of data. And after some data selection and quality control, so we finally got 3,600 earthquake with over 2 million of measurements in the P wave peak amplitude and S wave peak amplitude. And so we got a sufficient amount of data for regression. So we take the data and to feed for this scaling relation. So our goal here is to use our DARS measurement to find out the magnitude coefficient and distance coefficient, so as a site calibration term. And so first, let me show you how our data set looks like. So here I'm showing you the event averaged peak amplitude for both P wave and S wave, and how they vary with the magnitude and the distance. So different color correspond to different array. And so here is the magnitude, and here are distance, and for P wave, S wave. And you can see there are very strong and similar correlation between the peak strain rate and the magnitude. So as the magnitude increases, we get a larger peak amplitude, and also this peak amplitude decreases with distance. So we get further. So this is mostly the geometric spreading effects. And so that we can use this data to feed for our scaling relation. Since we have multiple array and multiple type of waves, both P wave and S wave, so we can flexibly use our data sets and in this study, we do the regression for P wave and S wave separately. And we also first do the regression with data from individual array. And also we can combine all entire data sets to do the regression. And so here are the best fit scaling coefficient we got from different array. And here shows the magnitude coefficient and for P wave and S wave, and so as the distance coefficient for both P wave and S wave. So each crosses correspond to the results from individual array, and the star are the results from combining all available array together. So from this result, we can see actually different array shares very similar value of those coefficient, this scaling coefficient. And yeah, so seems that different DARS array, they follow the same scaling relation. And here, I'm also showing you how the site calibration term looks like. So the background black line are from when we combine all DARS array, we can get this the site calibration term. And the red line are from fitting with individual array. You can see both match quite well. And another key information here is that you can see how this scaling relation how this side calibration term wire along the cable. So that's is another implication that the channel may be very different. They have very different side calibration term. So here the side calibration term here, for simplicity, we directly use one constant to account for all possible effects, regional effects, such as the instrumental coupling, the cable installation, construction, and even the local geological structure. Right, Brent? Yeah.
Well, I remember from the previous talk that the Long Valley cable is the nice, like very fairly consistent aerial, but so are those low, the site terms where they're really,
Oh, okay. So you're asking about those spikes.
is that like where it's crossing a road or something?
And those are mainly caused by the fiber loops.
Okay.
Yeah. So when we install the cable, when we got like more cables, so sometimes people just like put them together and hang there. So these part are not well coupled with the ground. So that's a cause for those spikes. And yeah, so yeah, back to the side calibration term. So from this, you can tell from the like looking at this old compilation of all data, you can tell like how different each channel may be. So even when they are very close, so their regional like side calibration term can vary like significantly. So this is kind of like, but for now we are still like keep working to have better explanation on this side calibration term to see if we can like separate the effects from different factors. But that's some work ongoing. So with the scaling relation, now we got the side term, we got the magnitude coefficient and distance coefficient. So we basically get the scaling relation. So we can reorganize the scaling relation we have. So that provide us an approach to estimate earthquake magnitude directly from the DARS amplitude. So we'll apply that to our data sets. So we use this scaling relation to estimate or predict the earthquake magnitude from DARS measurement and compare with the catalog magnitude. So here shows a comparison for the P wave measurement, and the right figure shows the result from S wave measurements. So we can see actually this scaling relation works quite well. So the DARS predicted magnitude is very close and consistent with the magnitude, the catalog magnitude, and the S wave works slightly better than P wave. And in general, they have the arrow like within one order of unit in magnitude. And you may notice that there are some like magnitude got overestimated. So that's actually caused by the waveform overlapping. For example, here we have in the Long Valley area, we have a magnitude 6 earthquake, and just 8 seconds before that, there's a 2.1 earthquake occurred. So the waveform of these two events just got overlapped. So that's why we got this significant overestimation on these small events. And others are almost the same, either due to the waveform overlapping or the signal from two events like arrive at the same time. So that can change that. But in general, this scaling relation works quite well. So
Question.
yeah.
What about the underestimated?
Okay, that's a good question. So these underestimation are often caused by like incorrect picking of the event. So it may not. So this for these two events. So sometimes we pick the wrong events or got happen to pick some strong traffic signal. So that can cause that. And for larger events, if we got underestimation, so that's often caused by the clipping. So here for sake of that, I didn't cover that, but yeah. So there's some reason for those underestimation. Yeah.
So for the catalog magnitude, they have a cutoff magnitude at 2, right? So they don't have any.
Oh, okay.
Right?
Yes.
In your catalog, you have smaller magnitude.
Okay. So that's because the data selection. So I checked the data set. So I basically remove all events below magnitude 2 because I find they are heavily affected by the local noise, and because of that, they seem to follow a different scaling. So I checked that. So that's why I removed all the earthquake below magnitude 2. But for the using our like DARS measurement, sometimes it got lower estimated magnitude, like below 2. Yeah, so far we find that the scaling relation works quite well within our data set. So next we will, yeah.
Why do you think it's working better for the S2 compared to the P?
Yeah, for P wave, because I feel like for P wave, so in general, the amplitude is smaller. And so when it's like mixed with the local noise, so it got like easily affected by the local noise. So that's why you can see actually for lower magnitude events, especially here, so it has larger error. And the signal to noise ratio of P wave is not as good as S wave. I think that's the main reason for this.
What's the depth range?
Depth range.
Like of these earthquakes, is there a limit or you just took all that?
I just took the entire catalog and did a few like data selection, did based on this. First is the signal to noise ratio and also the magnitude and basically the entire data set from the Southern California seismic network.
Jiuxun.
Yeah, mostly like about 50 kilometers. Yeah. Yeah, so next week we test a recent earthquake occurred a recent earthquake in Ridgecrest. So this is magnitude 4.6 events, and it's not included in our regression. So it's a very good event for us to test if this scaling relation only works for the data set or it can work for some new events. And we test this event in like pseudo real-time sense. So basically we assume that we have the streaming DARS data coming in, and we only use the available data at that each time step to estimate the magnitude to estimate earthquake magnitude like in real time. So this is to mimic the earthquake early warning system works, how earthquake early warning system works. And here for simplicity, we assume that we can immediately detect and locate events. So basically we know the distance and we know when the earthquake occurred and when to start the system. And the event is occur at here at 0 seconds. So that's the origin time of the event. And you can see like before 2.5 seconds, the wave didn't arrive. So the system does nothing. And since we don't detect any phase arrival, and but at 3 seconds, so that some channel begin to detect P wave. So then that's when we can like turn on the estimation, and we can for each available channel. So we measure the peak amplitude and use a scaling relation to estimate the magnitude at each channel. And we take the average value for with all the available channel to get the final magnitude estimation at that time step. So as we got more data, for example, like at 4.5 seconds, the P wave got detected at all the channels. So we begin to get a very good estimation and using the scaling relation for P wave. And at 6 seconds, that's when the P wave detects at all channels, and some channel also get the S wave. And so for those channels, we also take the S wave scaling relation to estimate magnitude and take the average of P wave and S wave estimation as a final estimation. So you can see actually here, once we got all the P wave, we already get very good estimation on magnitude, almost like the same as the catalog magnitude. As we got more data, so finally the magnitude estimation got stabilized, and so once we got all data, so we got a final estimation on this magnitude. And from this pseudo real-time test, you can also see that this entire workflow doesn't require lots of time to get the magnitude estimation. We only need for this case, we only need about 2 seconds to get a very good estimation on the earthquake magnitude. Yeah, and the next I would like to talk a little bit about the generalization of our DAR scaling relation. And for now, so far I have shown that the scaling relation works well for the California DAR array. And another important question is this DAR scaling relation transferable? So that means if we get a scaling relation from one region, can we transfer that to a new region? And so the motivation to do so is that we want to test if the scaling relation is universal for different regions and different tectonic environments. And we also, for practical purpose, so we also want to know if we can quickly build a local scaling relation for the data array in a new region with only limited data. And based on the prior knowledge we get from some well-studied region. So we do so by testing the scaling relation on a totally new data array in Japan. So we got some data from the submarine DARs deployed in the Sanriku region in Japan. And after some quality control and data selection, we finally got 48 earthquake with about 35,000 S-wave measurement. So here I quickly show you how the submarine DARS data looks like. So because of this cable deployed in the ocean, so it can record lots of ocean waves. So sometimes we had to apply a high pass filter to remove those ocean waves. And after that, we can see some earthquake signal. And even when we use the high pass filter, we still for most of the events recorded by the Sanriku data array, we can hardly see the P wave arrival. So we only use the S wave peak amplitude here as a validation for our scaling relation. And so, so we first take our measurement at the Sanriku array and only use the data from this array to feed for our scaling relation. So here I'm showing by the blue crosses shows the coefficient, best fit scaling coefficient we obtain from the Sanriku data array. And you can see the magnitude coefficient feeds are very similar to what we get from California array. And the distance coefficient is slightly smaller, a little bit different, but they are not quite different. So that's the information we got. And there are also some trade-off between those parameters. So next, we trying to directly transfer the scaling relation from California array to the Sanriku array. Since this coefficient, the magnitude coefficient and distance coefficient, they are not so different. So how we did that is we fix this magnitude and distance coefficient using the value we got from California data arrays. And with that, we know the magnitude coefficient and distance coefficient, but we still need to find the local site calibration term. So to do so, we randomly choose a small number of local events and take their measurements to constrain or estimate the site calibration term. So here shows you the site calibration term we got by using 6 out of 48 randomly choose events in the Sanriku region. So with that, so we can estimate the site calibration term. And so now we got every information we need to build a new scaling relation or transfer scaling relation in the Sanriku region. And so that's what we get. So next we use the remaining data to test if the scaling relation, transfer scaling relation works. And so we do so by comparing the predicted magnitude with the catalog magnitude. So here the red dots shows the 6 events we use to build the transfer scaling relation. And background image shows the other remaining 42 events. And we find actually they are very consistent. So with this a few events for the site calibration and the remaining events, the magnitude of remaining events can be correctly estimated within 1 unit or half unit of magnitude for most of these events. So basically this transfer scaling relation works quite well for a new region in a totally different tectonic environment in this subduction zone. And so finally, I very important question you may ask is how many events we need to calibrate this sine term, because if we need a lot of events to do so, so it's definitely not good for us to transfer that. So we do so by like measuring the good estimation, the percentage of good estimation. So here the good estimation is defined as if the difference between the DARS estimate magnitude and the catalog magnitude is smaller than 0.5. So we call that estimation or good estimation. So we do so for all the events and count the percentage of good estimation and use that as a quantification to measure the performance of transfer scaling relation. And we, for each, we did a lot of random tests. So each gray dots correspond to one random test, basically randomly choose a few events from our data set to fit for scaling relation and measure the good estimation. So we find that actually we don't need a lot of events. So only 5 or 6 events can already like provide us very good estimation and very good and transfer scaling relation. And here I'm showing you another extreme example. So for this case, we are very lucky to get like 3 events with very good data quality so that we can well constrain the side terms. So, and you can see these 3 events are in very narrow magnitude range. And even with that, we can build very good scaling relation that works for all other remaining events. Yeah, so to conclude, so in this study, we develop a data-driven method to directly use DARS amplitude to constrain the earthquake magnitude. So this is the scaling relation we get. And so, and by testing this scaling relation in different data sets and different array, we show that the scaling relation of DARS peak amplitude is transferable and possibly universal because it works for other and also works, not only works in US, California, but also works in Japan. And recently I'm also testing the scaling rate, applying that in Chile, and it still works. So basically I'm very confident about this scaling relation.